Welcome, everyone, to the colloquium of the Geneva Symmetry Group. Today's speaker is Federico Viglione, who is a postdoc at the University of Milan, working in the Cosmos project. Before joining that project, Federico was a PhD student. After, I guess, BA and MA studies in philosophy at the University of Torino, he went to Spain, to the Autonomous University of Barcelona, where he did a PhD in philosophy. Federico has some publications bearing on the dealing with the issues he's most interested in, which are generally philosophy of science, philosophy of physics, but more specifically the history and philosophy of cosmology, and even more specifically than that, the origin of the universe. Today, we're going to hear from him how to traverse the infinite starting now. Please, Federico.
Thank you. Great introduction. Thank you. First, a brief clarification about the title of the talk, because the reference to the now.
Sorry for this. Does someone have it in this room? But we don't know why.
But I remember that from slideshow, right?
It really only happens for the talks.
Okay. So the word now here has only the scope of making the title a little bit more catchy, but the word is not charged for any metaphysical relevance here. So the title may just be how to traverse the infinite starting at some time. But that it will sound less motivational. I don't know. So anyway, having said that, in this talk I will present an unpublished work, which is sort of a follow-up on a work that I published last year, where I argued that there seems to be no good reason to think that a traversal of the infinite starting at some time is either logically or metaphysically impossible. Where by traversal of the infinite, I mean the completion of an infinite series of equally long successive additions. In this talk, I proceed one step further, so to speak, and I argue that some physically reasonable models of general relativity may give us some reasons to think that a traversal of the infinite starting at some time is also physically possible, at least in what I call a proxy fashion. And I also advance a conjecture based on a speculative but somehow physically reasonable cosmological model, which is namely Cyclic Conformal Cosmology by Roger and Penrose, that it may also be physically possible to traverse the infinite in a non-proxy fashion, so to speak. So, so let me start by talking about the work I've done in the previous paper, specifically by giving you some context on the motivation of the talk and the results I try to argue there. Then I will go to the, let's say, discussion of the physical possibility of the traversal of the infinite by considering some general relativistic solutions, namely Malament-Hogarth spacetimes. And in the third part, I will talk about cyclic cosmology. So what the recent paper was about was concerned with the traditional argument, which is called the successive addition argument, which goes as follows. It's an argument for the finitude of the duration of the past. And it says, if the path of the universe is infinite in duration, then the temporal series of past events is actually infinite. An actually infinite series cannot be completed by successive addition. The temporal series of past events is completed by successive addition. Therefore, the temporal series of past events cannot be actually infinite. Therefore, the past of the universe is finite in duration. So the history of this argument is very old. It traces back to Philoponus and was also part of the first antinomy of pure reason. And this is the contemporary formulation, which is discussed by mainly some theologians. But I should already clarify that the argument can be resisted on several grounds. To begin with, one could argue sort of in a Kantian fashion that the argument is simply invalid insofar as 5 does not follow, because 1 and 4 may allow one to infer that it is not the case that the universe past is infinite, but this does not straightforwardly imply that the universe past is finite, because, for instance, its duration may be indeterminate, metaphysically indeterminate. Moreover, an additional commitment comes with premise 3, the premise that the temporal series of past events is completed by successive additions, because it's widely acknowledged that it commits one to some kind of dynamic view of time. But contemporary criticism has mostly focused on what we can call the most controversial of the argument premises, which is premise 2, which is also the one I will focus on. So why should it be impossible for an actually infinite series to be formed by successive addition? That is, by adding its member one by one. Or, to put it somehow more evocatively, why should it be impossible to traverse the infinite? So, definitives who propose the argument as the owner of the proof, but let me clarify the terms that appear in this premise. So, an actually infinite series, I mean, what is meant is an ordered collection, which is a non-mathematical multitude, possessing Aleph 0, so countably infinite elements, that can stand in one-to-one correspondence with a sequence, which is obviously a linearly ordered discrete set. That the series is completed by successive addition means that there is a time such that all the elements of the series have been added up one after the other in a given order, so that each element x that belongs to the series, except the first one, there is for each element x that belongs to the series, there is an element epsilon such that x was added immediately after epsilon. So here you see the condition stated a little bit more formally. What 2 states basically is that there can be no time where this addition completed condition holds for an actually infinite series. So there can be no time where all the elements have been added up in the past, one after the other, and the series is now complete, so to speak.
Sorry.
Yeah.
Yeah.
Feel free to interrupt.
Sorry.
The predicate high is, sorry, I didn't put it in the slide, having been added immediately after. Okay, so what the condition says is that for every element of the series, there is an element, if it is not the first element, that's the antecedent, then there is an element that precedes it, such that has been added immediately, such that x has been added immediately after epsilon, right? Can you see that?
Yes.
So it's basically for every element of the series there is a preceding element such that x has been added immediately after that. That's just and if this condition holds, at sometimes it means that all the elements of the series are such that they have been added up just after the previous element.
Yeah, I think I struggle with understanding this very temporally loaded way of speaking about this, having them added.
Right. So
but this.
So this is sort of semi-formalization. Of course, you could use a temporal logic to make it more right, but was just to give a formal condition. So good. Yeah. Yeah, go ahead.
So is it wrong to characterize the formal condition just as saying that everything has an immediate predecessor? I mean, that's how I just reading the statement.
Not
Everything,
so,
if it has a predecessor, then it has an immediate predecessor.
not really, because the point is that it has been added up. So there is a dynamic element, right?
Exactly. Just reading the statement, right? I can't.
So yeah, because I didn't define the I, because I forgot to put it in the slide, but the way in which the predicate is defined, having been added up immediately after, is intended to give a dynamic understanding of.
So
right?
It's not just that there's nothing in between,
No.
but it's really
No.
the dynamic
exactly.
of the eye.
Exactly. Okay. So the point is, for the people proposing this argument, there is no time where this condition holds for all the elements of an actually infinite series with zero. Okay. Thank you for noticing the. Okay. Okay. So and also the modality, as we said, is usually taken to be logical metaphysics. So now these are the examples of some of the examples of the kind of things that are logically or metaphysically impossible according to the premise 2. For instance, they say that it's impossible that there is a time such that one has finished counting one by one all of the countably infinite elements of an actually infinite series, or that there is a time such that one has traversed the path of countably infinite tiles, or given a dynamic view of time, that there is a time such that all the countably infinite events that compose the universe path have already actualized one after another. But why should we consider these things impossible? Because obviously, prima facie, there is no contradiction entailed in these scenarios. Many opponents, starting from Russell, remark that at least in the case of an infinite count with no beginning, this is not a logical impossibility. So what the proponents of the arguments do, sometimes surreptitiously, sometimes more explicitly, is to refer to what I call the first addition claim, which is the following claim. An actually infinite series cannot be completed by successive addition of equal finite duration, starting with the first addition. And this is taken to be a wholly uncontroversial claim, even for the opponents of the successive addition argument. For instance, Morriston, who's a critic, maintains that it is wholly uncontroversial that there can be no time at which the infinite series having a beginning has been formed by successive addition. Now, seeing that this first addition claim is uncontroversial, finitists have had the tendency to propose arguments for premise 2 based on this principle. For instance, Whitrow argued that when one tries to form a series by successive addition, one must start with the first addition. And also, Stephen Poore here represented what a so-called rule by symmetry, by which if it's impossible to count all the elements starting with 1, then it's impossible to all the infinite elements of an infinite series starting with 1, then it's impossible to do that finishing with 1. And there are more examples. Since all the participants in the debate agree on this principle, and usually one needs auxiliary assumption to deduce the premise that the proponents of the arguments are interested in, then the debate has focused on the auxiliary assumptions. Instead, my aim is to directly criticize the first addition claim, both in the logical metaphysical interpretation and in the physical one of the modality of the claim. So let's start from the logical interpretation. The reason why this claim is commonly accepted indeed is that it seems true by logical necessity. How could anyone ever finish counting infinitely many numbers by starting with the first number, for instance? However, consider a sequence that has two termini and countably infinite elements. This is not a common setting, but it can be done. Consider, for instance, the set of all the integers on this particular ordering. Basically, what we have is all the positive integers, 0, 1, 2, going forward, and then all the negatives until -3, -2, -1. So this series, I call this order type omega plus omega alpha. And this sequence is still discrete according to the standard definition of discreteness, because all the elements of the sequence that belong to it are isolated. So this is still discrete. And now we can suppose that an actual infinite series has this order type. For instance, each number could correspond to a certain event. What I claim is that we can suppose that each member of this temporal series, so non-mathematical series of events, for instance, has been added by equal successive additions, so that the additions in the series occur in the specified order. Because recall the addition completed condition. All that states is that for each element in the series, there is another element that was added immediately before it. And this condition can be respected, for instance, at this time, if, okay, let's see, you nodding, so I won't stress this. So what I concluded is that it is consistent to suppose that this series is formed in the specified order by successive addition. And this contradicts the first addition claim in the logical interpretation of the modality. What about the metaphysical interpretation? So, to maintain that the first addition claim is true as a matter of metaphysical necessity, how am I with time?
So you're
halfway through? Okay.
yeah, a little bit less.
Okay, perfect. So, to maintain that this claim is true as a matter of metaphysical necessity, one should argue that an essential property of infinite series entails that they cannot be completed by equal successive additions by starting with the first member. And there is no argument such that, and the onus of the proof is on the infinities, so one could just wait and see what happens, but I think I can offer some considerations. So I think the main reason why this it may seem impossible metaphysically to begin counting all the countably infinite integers now and complete the task later is that the number aleph 0 is a transfinite number, right? It does not belong to the set of integers. So it is true that if I begin counting now in a finite number of utterances, I will have counted a finite number of integers. And similarly, if I start walking now in a finite number of steps, I will have made a finite number of steps. But all this entails is that there is not a determinate step at which the number of my steps becomes infinite. Rather, that I cannot make aleph 0 steps at all. So traversing the infinite by starting somewhere would require, therefore, that it is possible that there is just no determinate step at which the total number of steps becomes infinite. It is just that on the left side, let's say, you have made a finite number of steps. On the right side, you have already made an infinite number of steps. And there is no determinate step at which you make the switch. So one, to deny that this is possible, one should find a reason to think that a determinate step is metaphysically necessary. But given the nature of infinite sets and infinite series, I think it is more reasonable not to require a determinate step. And we can enter more in that. But For now, let's say that I conclude this part that was about the previous paper, and I pass now to the physical traversal of the infinite. So the idea that, okay, so should we at least accept that one cannot traverse the infinite by starting with the first step, in the sense that this is a physical impossibility? I believe not. So if one trusts GR in having a say on what counts as physically possible, and let's assume it does, then one simple way to put the question is as follows: are there reasonable solutions to Einstein field equations allowing for a traversal of the infinite that satisfies some reasonability criteria? And the first thing one must notice is that some relativistic solutions are straightforwardly compatible with counterexamples to 2, which was the main premise that was supposed to be deduced from the first edition claim, right? Because, of course, many relativistic solutions are geodesically complete, meaning that any inextendable geodesics in the manifold is infinitely extended in both directions. And therefore, it becomes possible to conceptualize an ideal observer performing an infinite series of equal successive additions along a timelike geodesic gamma up to a certain point P. Easiest counterexample Minkowski spacetime. However, past finities have a ready answer for this, because given the successive addition argument, which is a purely philosophical argument, they contend that we should not consider relativistic solutions depicting infinite past as representing physical possibilities. One such paper was by Ellis, Kirchner, and Stöger, and they say, we emphasize that the problem with infinity is not primarily physical in the usual sense. It is primarily a conceptual or philosophical problem with the idea of a realized infinity. So to see that the philosophical problems pointed to, this is just a passage of their paper, they do not enter in the discussion, but if we take another paper, Stöger, we see that the philosophical problems they are referring here are actually the successive addition argument and the first addition claim mentioned before. Because Stöger writes, defenders of an actual infinite past argue that though it is true that it is impossible to conceive constructive an infinite past by successive addition of moments, that is simply because we are still locked into thinking of doing it in a finite time. We need to realize that this is done only in an infinite time. This reply, however, still seems lame, simply because there is no way of definitely conceiving a completed infinite series of moments, even in infinite time. We just do not have the capacity to model a completed infinite time. All we have is the concept of a series of moments which continues forever without end and without definite completion, right? Without ever reaching a point at which it has already been going on for an infinite amount of time. So it seems to me that the argument here is just that since we cannot model an infinite series of equal successive additions, because we must start at some point. It's not that we cannot not have a space-time model that represents it, it's that we cannot model it dynamically starting with the first element. Then we cannot conceive a completed infinite series of equal successive additions ending at some point, as it will occur if the past were actually infinite. So again, there is the first addition claim coming back from the window. So as I hope I showed, it is possible to conceive an infinite series with both a beginning and an endpoint. But well, we can come back on the interpretation of this passage. But what I wanted to show that again there is surreptitiously the use of this first addition claim even in the philosophy of physics literature. And so let's see what we can say about the physical. Well, that would be FAC P, the physical possibility of the first addition claim. To shake it also the safe ground in that supposedly safe ground in that respect. So the most natural counterexample to the first addition claim coming from relativity are Malament-Hogarth spacetimes. This point has already been noted also by Daniel Lingford in a paper that is forthcoming, but there are some nuances, so I will spend a little bit on it. So a Malament-Hogarth spacetime is commonly defined as a relativistic spacetime, which I mean, it is Malament-Hogarth if there is a spacetime point such that there is a future-directed time-like half curve that is completely in the causal path of this spacetime point. Okay, so you can see, for instance, the most intuitive example of a Malament-Hogarth spacetime are anti-de Sitter spacetimes, where we have a spacetime point P with a past light cone, the boundaries of which are bending because spacetime is curved, kind of like a cylinder. And so the half curve gamma approaches the boundary of the past light cone, but never crosses it and never reaches it. Okay? Is this part clear? So other classic examples are specific black hole solutions, such as a rotating Kerr black hole, also spacetimes with closed time-like curves, right? So what they have in common is that you can have an infinite half curve within the past, the causal path of a spacetime point. So also in the case of closed time-like curves, imagine you're traveling along a closed time-like curve, so you could go on for an infinite time without ever reaching a spacetime point that is in your causal future, which is, however, maybe reached by someone by some other observer that doesn't travel in closed time-like curves. So these kind of spacetimes are often discussed in the context of supertasks or hypercomputation. And this is because in these spacetimes, an ideal observer, which is the sender, it's called the sender, following gamma, could in principle perform an infinite number of tasks. Say, it could check every positive integer for a mathematical conjecture, and eventually communicate the output to a second ideal observer, which is called the receiver, who instead follow a different word line, and so only experience finite proper time. But if now you can see maybe that if Malament-Hogarth spacetimes represent physical possibilities, then the first addition claim is false on the physical interpretation of its modality, because the sender could just take this, the same proper time to perform each task, you know, and they start with the first task, and at P, the receiver can say that the addition completed condition holds for the series of successive tasks that has been performed by the sender. Good. So is this point convincing? See, nodding. Okay. So the philosophical debate on Malament-Hogarth spacetimes has produced much material in the attempt to establish whether this kind of spacetimes are physically reasonable. One important shortcoming is that they are not globally hyperbolic, because it has been proven that they cannot be foliated by Cauchy surfaces. This is a general theorem for Malament-Hogarth spacetimes. However, there are some authors, such Herman, Hogarth, and Manchak, who have also argued that global hyperbolicity is too strict of a criterion for physical reasonability, and I also tend to agree with that. And in fact, many Malament-Hogarth spacetimes are stably causal. So, such that no arbitrary small perturbation in the metric introduces closed time-like curves. A different issue is the so-called blue shift problem, because in certain Malament-Hogarth setups, the sender is assumed to send infinitely many light-like signals to the receiver. But if you take some further reasonable assumptions on how the signals are sent, one can show that the frequencies of the recorded signals diverge. So that in the end, the total energy carried by the signals P is infinite. And also there is a problem with acceleration, because in some Malament-Hogarth setups, such as in the anti-de Sitter case, the total integrated acceleration of the sender is infinite. And therefore, once again, the receiver at P can say that an infinite amount of total energy has been expended. How decisive are these problems for the physical possibility of Malament-Hogarth spacetimes? Not very. Because neither the blue shift problem nor the acceleration problem occur in every Malament-Hogarth space setup. For instance, Manchak has built a Malament-Hogarth setup where it is possible to escape both, while satisfying some other conditions for physical resolvability. Moreover, the blue shift problem is not concerning at all for my purposes, because it is important in the context of the discussion of supertask, because communication is crucial. But this is not the case for the purpose of suggesting that Malament-Hogarth setups are genuine counterexamples to the first addition claim. Because independently of whether the sender and the receiver can communicate, it's still true that at P, the addition completed conditions holds for the infinite series of successive additions of the sender, right? So if there is a Malament-Hogarth setup is such that only a finite amount of energy is consumed by the sender, the spacetime is at least stably causal, then one may have a good candidate for a physically reasonable counterexample to the first addition claim. Okay, so much for counterexamples to the first addition claim. However, consider again the case of an infinite series of tasks performed by the sender. At no point the sender can say that he has completed the series of tasks, right? In this sense, Malament-Hogarth setups can be said to represent cases of what I may call a proxy traversal of the infinite. It's true that it's completed, but only always by another ideal observer with respect to the one that can state the addition completed condition. Therefore, it raises the question, are there spacetime structures that provide grounds for a non-proxy traversal of the infinite with the first step? If so, one will have a counterexample to the first and last addition claim, which is stronger than the first addition claim, where that is the claim that you cannot complete an infinite series of equal successive addition by both starting and finishing at some time. And this would directly be a direct strike against the successive addition argument, because the falsity of this claim entails the falsity of the claim that one cannot complete an infinite series by ending of a successive addition by ending with the last one, which is the claim that the proponents of the argument are ultimately interested in, since they think that an infinite dynamic path would entail that an actually infinite series would have been completed just now, so it would need to have the last past event. I suggest that in order to find a counterexample to Flack, one must leave the realm of classic solution of Einstein field equations and look at cyclic conformal cosmology. So this is the part that is still sketchy and on which, let's say, I'm still working on. So from now on, please forgive me if I say something that for you is obviously wrong, but I will try to make my point without complicating too much things. So this speculative model, first of all, has the merit of explaining or providing an explanation for the low entropy initial condition of the Big Bang, and it also suggests some testable predictions. So these are reasons why we should take it into consideration, I think. So to build it, one starts with a suitable cosmological solution of Einstein field equation with a positive cosmological constant, which admits a well-defined cosmic time function and features an initial singularity and an infinite period of exponential expansion in the future, such as FRW models. Then, by conformal rescaling, one can extend the conformal space-time geometry at and beyond the boundaries by stretching the metric by a conformal factor, which tends smoothly to 0 at the future boundary, so that an infinite space-time region is rescaled to a finite one, and it is allowed to become infinite at the past boundary, so that the singular region in the is rendered finite and smooth. So notice that this is not just a mathematical trick up to scale down or infinite regions or scale up small regions. In this model, the null geodesics reaching the endpoint at infinity that actually does acquire a physical meaning. Why? Because this was the right one. Because the crucial speculative hypothesis in cyclic conformal cosmology is that given enough time, all massive particles will eventually decay, so that their total rest mass approaches 0 to the limit. Moreover, Penrose also is quite clear that the rest mass of particles effectively reaches 0 prior to the future space-like boundary. So that we have what we may call a conformal error. Because, so Penrose thinks that space-time lengths are fixed only when massive particles are around. So in a slogan, when only massless particles are present, the universe, he says, loses track of the scale of time. The metric becomes conformal. Effectively conformal, this is important. Moreover, Penrose identifies this future space-like boundary with the past space-like boundary of a successive period of expansion. He calls each period an eon, and the result is an infinite series of eons, the end of each eon being smoothly and causally connected with the beginning of the next. So each eon is represented as a relativistic spacetime, while the whole series of eon is described by a single conformal metric, to which all the physical metrics are conformal. Now, well, Baptiste, for instance, has argued that maybe another interpretation of the model would be to have just one eon that is repeating in a cosmic loop. But this is actually not important for my point, because in any case, there are no eons that are infinitely far apart from other eons. However, according to the model, in each eon, massless particles are said actually reach and cross the future space-like boundary, which becomes space-like because of the expansion. So would be lifelike. So by using Penrose's words, to massless particles, the ultimate hypersurface represents a region of their conformal spacetime that seems to be just like anywhere else. And there appears to be no bar to their entering an hypothetical extension of this conformal spacetime on the other side of the ultimate hypersurface. So that, I mean, at least prima facie, it seems obvious that the traversal of each ion by massless particles can be characterized as a non-proxy, as I called it, traversal of the infinite. But are things so simple? No, actually, it's the opposite. So, well, let me offer my point of view on the matter as it is at the moment, but it changed like half an hour ago, so it can change in half an hour. So according to relativity, we know that the proper time we know that the proper time along null geodesics is always 0. Therefore, one can say, well, okay, then massless particles traveling on null geodesics do not actually traverse an infinity of times, since 0 proper time has elapsed on the null geodesics, and that is okay. But another thing is to say that they have not made an infinity of steps. In fact, one could argue that each take whichever 2 points, 2 space-time points connected by a null geodesics. If you can model that as a series of countably infinite steps, each will have the same, as for instance, with the omega alpha series I presented above, then one could say, well, each has the same equal length, which is 0. And that would be a counterexample to the first and last addition claim. But of course, this is rather unsatisfactory because the proponents of the successive addition arguments will say, well, I just rephrase FLAC as require equal non-zero finite duration, because to say that something is successive steps of 0 length have the same length is kind of weird. And also, more importantly, they will notice that when it comes to null geodesics, physicists usually make use of a different kind of parameters, which is an affine parameter. So they will likely argue that affine length is the relevant notion of length when it comes to null geodesics, and then it is not true that any null geodesics can be partitioned in countably many subintervals of equal finite affine length up to the future space-like boundary. Or in general. So I think it is at this point that cyclic conformal cosmology becomes relevant, and then I conclude because I think I'm almost out of time. Because affine parameter is not the only kind of parameter that has some physical meaning in parameterizing null geodesics. Another parameter that is not non-affine, and so it makes the intrinsic acceleration of the massless particle non-zero, but this is actually a mathematical artifact, is a parameter that can be used, that can be defined in reference to the scale factor. And now let me read this passage from Penrose. Here Penrose is thinking about, so he said, well, at a certain point, black holes will evaporate, and all that will remain available around will be single massive particles slowly losing with the rest mass slowly approaching 0 in the limit. This is the speculative hypothesis of the model. So it is not that during that era there will be no massive particles around at all. It's that locally the metric will be conformal, but there will still be massive particles around slowly losing their rest mass. And he asks, is concerned with how to preserve, the metric of the expansion that gives you the expansion of the ion up to the future boundary. And he asked, in order to preserve some appropriate form of Einstein equation with constant lambda through the entire history of the eon, we need to use another proposal to scale in the metric rather than using the one from new geodesics. What we can do, another proposal he was thinking about tracing time following one single particle, like an electron or a photon, and or a proton, and he says that's not possible because it will not give you the expanding metric. What we can do, although this will hardly be a practical solution, will be to use lambda itself to determine a scale of what appears to be closely related to this. We might use the effective value of the gravitational constant G. Then the picture of the evolving and unendingly exponentially expanding universe is retained, without seriously disturbing the philosophy that locally the universe will eventually lose track of the scale of time. So what is saying that during the conformal era, although the metric is locally conformal, we can still use the scale factor and lambda to globally keep track of time. And so we could also use that to define a non-affine parameter along null geodesics, right? So if that is true, then since each eon is future null complete, every geodesic can be extended into the future to an indefinitely large finite value of this number. Let's call it scale factor parameter. And so this will constitute actually a counterexample to the first and last addition claim. Okay, so to conclude, we have seen that some philosophers think that relativistic models describing an infinite past should not be considered physically reasonable for philosophical reasons, that is, for considerations connected with the successive addition arguments and the first addition claim. However, I analyze the philosophical arguments and I find them unsuccessful. Moreover, once these philosophical concerns regarding metaphysical possibilities are set aside, one finds out that relativity allows not only for the possibility of a traversal of the infinite that never began, such in Minkowski spacetime, but also for the possibility of a traversal of the infinite that began at some spacetime point in Malament-Hogarth spacetimes. And according to a speculative cosmological model with testable prediction, we could also suggest that it is possible to, for some special kind of things at least, to traverse the infinite by both starting and finishing at some times in their own working. And yeah, that's it. Thank you.
Questions?
Yeah, thank you very much. So I'm struggling a bit to see what pull this successive addition argument is supposed to have. So why should a traversal in that sense be required to be physically, like infinite past, to be physically possible or even realized? So because by this notion of traversal, we start our traversal and then possibly infinitely, I mean, very, very, very much later. But why should there be the starting of the traversal? If I think of, okay, yes, there's an infinite past, which is just like omega star, so it's just going infinitely. There's no first moment. And of course, then there's no moment from which I can start and then go into the future and ever reach that and now. But I could from now just go infinitely to the past. We're infinitely long in the past, and of course never reach a point at which I traverse infinity. But that's yeah. So I don't really see why this traversal should play a role.
Yeah. Thank you for the question because it allows me to clarify a crucial point. So these are actually two separate issues. So what they want to say, these people proposing this argument, is that the past cannot be infinite in this sense, right? Omega star sense.
Yes.
Okay. So first of all, they have to assume that time is dynamic somehow, because of course, if time is, if the you have a eternalist for the view, then what's the problem? But if things have been adding up somehow dynamically, then you sort of rise this problem. This is the beginning of the discussion. You ask, okay, so we can build that logically. We have a mathematical series represented that. We have physical models represented that. What's your problem? And they say, well, we have metaphysical reasons because why? So one of the main things they say is that, well, of course, everyone agrees we cannot finish counting all the infinite numbers starting now. So they argue for some complicated rule of symmetry and say, so it's also impossible the opposite thing. And all I wanted to argue was, so people have focused on saying, no, but this auxiliary assumption, you're ad hoc or whatever. But what I say is that, no, you can also finish counting by starting somewhere. And why not? I mean, so first of all, you can model it, so that's not logically impossible. And second of all, this is discrete. And again, give me a reason, just like in this case, right? Give me a reason why this should be impossible. Give me a reason why this should be impossible.
Yeah.
I don't know if I answered you.
Yes, so that's already helpful that it's really, so it doesn't the dynamical of time. I don't see it because, well, it has just been dynamical for infinitely long there.
I agree with you.
Yeah.
Yeah.
But yes, that's it. But don't you think that then the reaction would be, well, okay, this is of course a full construction, but it's also cheated in the sense because what we meant is that there can be no first moment of time, and if there's no first moment, then really you cannot traverse it.
No, I think so some arguments are based on not there being a first moment. Like for instance, arguments based on the idea that if I have no first moment, then at any moment an infinite series should already have been completed. And I say, okay, the infinite series is completed now. And why not before, right? The Leibniz question. But I think that's a different family of arguments, which one has to answer differently, namely by saying, well, that's maybe just a brute fact, right? It's like you meet a person counting back all the numbers from infinity to zero, and they go like -3, -2, -1, 0. And you ask, why didn't you finish before? If you're counting from all eternity, and they say, I don't know, I've just been counting and I finish now. That could just be a brute fact. But this is a different family of arguments. The main arguments I was concerned with were the ones that were kind of implying that since we cannot start, then we cannot and count all the infinite numbers, then we cannot even finish. Yeah.
Yes, thank you. So the reason why I'm afraid your model wouldn't maybe move some components of these arguments not that much is that I guess if time is actually continuous, then these kinds of cases where we have infinitely many things between two, that's actually ubiquitous. But really what we find problematic is that there was no first one.
Right. So, first of all, thank you for the question, because this is also important to stress. This is not continuous, right? This is discrete.
Exactly, yes.
And I think that if you are ready to accept that this can be the model of a temporal series, then you lose the main intuition and perplexity behind just this, right? Because this is part of this. And of course, the main perplexity then is, well, what is this? Is this a gap? I don't think so. I think if we could write this over infinity, we will see no gap. But yeah.
All right. I guess we have the same or very similar questions, and we can maybe try to formulate them differently. But Think like I kind of like the last part, and I think it was kind of nice, but I was really puzzled by the beginning. Not because of you, but by this argument and this starting point using this idea of addition. Because so not only you have this kind of dynamical approach to time, it's discrete, you seem almost to conflate the mathematics with the physics, and you are counting is a process, a natural process unfolding in time. So it's a bit too, for me, it's a bit difficult in my own metaphysical framework to really understand why there should be the starting point and why we might want to be willing to traverse infinity this way.
Okay.
It was a lot easier for me to understand the cool questions about whether there could be some physical infinities, and
Yeah.
if yes, of which kind, and so do you think that's the right starting point to have this kind of
Right.
because to me it's striking honestly striking as a bad argument against the infinity of the past for many reasons.
Yeah,
So
I
do you
agree.
think that you might use a lot of the very cool things you say and connect them to a more contemporary framework?
Yeah, I actually do that in a sense that so the part that you're referring to is basically the new paper. And perhaps the part that is perplexing you is the old paper, which was concerned with this debate. And this debate, so this argument is very popular.
Yeah, but I'm puzzled.
And and it was in Kant. It has very old tradition.
It was before the current physics of time we have, the current
Well,
mechanics of time we
but the
have.
point is that the perplexity is not about the physics; it's about the metaphysics, no?
Yes. Yeah, I think it's very old-fashioned.
Yeah. So I agree with you that it strikes as a bad argument for many reasons, but it is very tricky when you start to think about the second premise and you just, you put aside the idea that if there are physical models with an infinite past, then infinite past is possible, full stop. Because there are like Alice and other people saying, no, well, also if there are models with an infinite past, we should consider these philosophical arguments and consider them non-physically reasonable, right? And so start to think about, okay, so what's the metaphysical reason for that? And I agree that with you that in the end, it's just a matter of recovering the initial intuition that, of course, over an infinite time, it's possible to complete an infinite series of successive addition, but it's slippery because, yeah, you have to face. But yeah, I agree with you that this part is more perplexing. Yeah.
I have a finger on that. So you repeatedly said now in Q&A and in the talk that this is a popular argument.
Yeah.
Is it a popular argument in the last 50 years? I mean, it has.
Yeah.
Really? So who has defended it?
William Lane Craig. Then there are other theologians that follow him because they all want to say that basically the universe began because God created it, right?
Okay.
And then the metaphysicians have started to discuss that. I'm trying to do that, but there are also a couple of other people. One is Malpass. We are trying to discuss that, separating the thing from the debate from theological interest, but of course they are very ambiguous in their formulation. So it's a tricky work to make precise the claim that they make and then decide. Yeah.
Thank you. Federico.
Yeah, thank you for the talk. I mean, I think it's changed the puzzlement of these arguments, but in the interest of changing topics, I'm going to ask you about the cyclic conformal cosmology thing, because it's completely unclear to me in which sense what happens to a photon in one of these models is traversing infinity not by proxies, or how we call it, right? Yes, I'm completely puzzled by that claim, because it seems, if I understand correctly, like the photon takes an infinite amount of time to get past to future null infinity, because it's a future null infinity, that's how it's defined. And then it goes over into this new eon where it just keeps on going, which in and of itself is a mildly puzzling feature. But it seems, if I understand correctly, the suggested solution is, well, sure, but don't look at the proper time. So don't look at don't look at the parameter on the word line of this photon. Just look at the parameterization in terms of the scale factor, basically. And that is a perfectly fine thing to do, and it's a completely allowed thing to do. It's just that it's the exact same thing that was happening in a Malament-Hogarth spacetime with the receiver. The receiver is the scale factor. The receiver is just a random degree of freedom that you pick, that you use to parameterize your so I'm unclear in which sense this
because differently from the Malament-Hogarth spacetimes, the null geodesics actually reaches the future infinite boundary in the model, right? While in the Malament-Hogarth spacetime it never reaches. There is no point along this curve.
You can put a boundary of that spacetime. You just
yeah, but there is so the point is that there is no physical reason to think you can represent it conformally, and so you can represent the conformal boundary and the output reaching the boundary, but there is no reason to attribute a physical meaning to the sender reaching the boundaries. Instead, in cyclic, sorry.
But of course there is. Of course there is physical meaning. I mean, not necessarily, but of course there is physical meaning. If you have an ADS spacetime with the boundary, so the compactified ADS spacetime, of course the boundary has meaning. Like if you send a photon, the photon literally bumps off the boundary. So if you're inside, you literally see a photon coming back.
Yeah, I see your point. So, yeah, sorry, you have to follow up. Oh, should I go? So what Perros says is that the reason why the massless particles reach the boundary is because at a certain point the universe loses track of time, so to speak. So it's because the metric becomes effectively conformal. So the idea is that, okay, so he says that clearly. This is just a mathematical trick to represent a boundary. It does not physical meaning usually, unless we have this speculative hypothesis that all mass or all rest mass eventually goes to zero. Then the metric globally becomes conformal, and then massless particles actually physically reach the boundary. If I had to, so I follow him on this, but if I had to say he's right or you're right, so for me, it would be too easy to say, well, yeah, the sender will physically reach the boundary sooner or later, because the obvious answer would be, no, that's a mathematical trick, the boundary, it's just, a limit, so.
No, I'm saying something, I'm saying something else, which is this. In the case of the Malament-Hogarth spacetime, the reason why you're saying this is only by proxy is because if I am the sender, it takes me an infinite amount of time to analyze the boundary. That is also true if the boundary is physical. It takes a photon. The photon perceives the sender would perceive themselves as taking an infinite amount of time to reach the boundary.
No,
the fact
it's not because it takes an infinite amount of time. It's because the boundary does not physically exist, so to speak. In conformal cyclic cosmology, the null boundary is actually space-like. It's
is it a null boundary or a space-like boundary?
It's space-like. The boundary at which null geodesics end up is space-like because of the expansion. And so it becomes physical in a sense. In this case, I would say the obvious objection would be there's nothing physical there, and it's just a mathematical representation. There is no boundary. So, not because it takes infinite time, but because structurally the universe is not made like that. I don't know if I.
So if I accepted that the boundary of an ideal space-time is physical, then you would say that that's time travel not by proxy.
Yeah, for me, it
Time
would,
travel infinite.
yeah, for me it will be fine. For me, it will be fine. But it will be, I think, difficult to define.
Nothing.
So my question is about how to define the past in GR. This is something that I guess you need if you're the receiver at P and you want to say that the action has been completed.
Mhm.
And I suppose there's a very natural answer, right? The past is the causal past.
Okay.
But I wonder whether there's a consensus on that in the literature, right? Maybe if I was some kind of hardcore presentist, right?
Mhm.
I want to have a privileged foliation, and I want to define the past as anything that's to the past of my privileged foliation.
Yeah.
So I just wonder whether that would make a difference, for instance, to the Malament-Hogarth space-time, right? Or, yeah.
So yeah, that's a good point. The reason why it's important, the reason why it is discussed, the causal past, is because the Malament-Hogarth spacetimes are important in the context of supertasks, right? So it is important for the sender to be able to always communicate with the receiver in order for having these as counterexamples of causal past. If I had a wider understanding of what counts as the past of P, and I say, well, past of P is just the whole set of hypersurfaces foliating the space-time, time-orientable space-time before P. And yeah, maybe there would be different kinds of space-times where you could have an infinite half curve completely in that past. Yeah, but I think again it would be. So personally, I'm not a friend of absolute simultaneity, and but I think it would be.
There is this view in the Putnam particle, right? I think that the kind of presentism that is just presentism about here,
the
right?
point.
Yes.
The
So
here
I
now.
guess in that case, past would be just on your world line, right?
Mhm.
And then maybe you would not be entitled to say the action has been completed, right? Because the action is not fully located in your past. So
Yeah.
I'm just wondering, yeah, what is actually the semantics of this statement in the relativistic space time?
Yeah, I guess this is the so this is the uncontroversial example, right? Because I think even Putnam would agree that. So for Putnam, he said, well, the present is here now, but he will not deny that JP is the causal past of that present, right?
Well, he would not deny that it's the causal past.
Yeah.
That's defined mathematically, right? But he might argue whether that is like the past of, right? Right.
Yeah. Why?
That is the way I think about it. The causal past is just one way to cash out precisely what being past metaphysically means, right? In GR.
Yeah, but the problem is that given you know the relativity of simultaneity, if you have a point that is space-time correlated to P, then depending on how you foliate, it may be in its past, it may not. But in the causal past, the relations, the temporal relation with P is fixed. That's the point.
What do you mean by temporal?
I mean that there is no foliation according to which a point in the causal path of P is simultaneous or after P. So I guess I think also Putman will agree that in that case that will count as a past an event happening here is a past event with respect to P. I think.
I hope that won't be long. I just want to add like a small remark to the first question after your reply to Chris's question about who actually endorses these arguments. So if it's theologists, then it seems to me what they care about really is this first moment, right? The moment of creation. That's what matters for them.
So what's interested them in they are interested in we could say having a first event
Yes.
that is caused by God. Yeah.
So
Not necessarily a first moment, right? Because the first event could be open on the past boundary, but a first event, let's say, could be extended open on the past finite duration, still first event, right? Like the Big Bang.
Usually they also think that time was created with the first event. So I think it's a logical option, but most theologians think that.
Yeah, but the first event does not need to have a first moment of time. It could be like the Big Bang. Usually they say it's not closed because they say, well, God created the Big Bang, and the Big Bang is let's say the first 10 to the minus something seconds of the universe, and it is open towards the past because time is continuous. So, but it is finite in duration, and so it's the first event, something like that.
Yeah. Well, I just wanted to point to that that then maybe your argument will just make them refine the premise, right? And say, okay, so you cannot traverse a series that doesn't have a start point, because that will still be true. And then they would maybe say, okay, thank you for the clarification. We were not very precise with what we meant with infinite here. What we care about is the
I don't think they will be happy with that because they so for instance William and Craig, he argues that there are he uses also paradoxes like Hilbert paradoxes to say that there are no actual infinities at all and stuff like that. So they will be very unhappy with accepting it. But okay, but thank you. It's a possibility.
I have a question. It seems to me that if one were to sort of ingeniously combine considerations from general relativity, where temporal orderings or temporal facts are not as they're naively assumed, perhaps including in this successive addition argument, that there may not be such a clear order of events, even whether finite or infinite or what have you, because the space just doesn't have that temporal kind of structure. It may be cyclical temporally, or all sorts of other, or combinations of this, different parts of space that may have different topologies in that sense, and so on and so forth. And you combine that with a little bit of Mate's considerations about what we mean by the past, sort of what's a metaphysically right way to think about the past. And then at that moment, at the latest, I think much of the successive addition argument falls to pieces. I just don't see how.
Which premise? So the whole argument, or
anything? I mean, what remains? I don't even know.
Right. So I think they move in that case. So again, I'm defending those who I wish to attack, but because I have also considered these considerations, and I think one move they could make is just to say, well, for instance, premise 2. You can just apply to every geodesics every time like curve, right? And you can say, okay, forget about So, well, then their official move will be no, the universe has to be time orientable. If not, it's not physically reasonable. But if they will not make that move, I think a possible move would be, well, but for instance, if I am traveling along a time-like curve, and you have a physical model where this time-like curve is unbounded to the past, but that's not physically reasonable because of this, which is precisely what Alice and the other two people say. And I think that's something you have to answer, right? Also, if you allow for time non-orientable.
Yeah, maybe we don't need to go all the way to
Mhm.
non-temporally orientable space times.
Mhm.
But for instance, premise 3 suggests that there must be some sort of dynamical process with successive addition
Mhm.
of something, of whatever,
Yeah.
of elements to the series or something like that. And in order for there to be a possible such dynamical mechanism in place, a certain temporal structure will have to be present, more than just an orientability, maybe much richer than that.
Mhm.
And one option would be to say, like, no, I think not all of these strong conditions of temporality are in place for there to be such a dynamical mechanism. Yet there are temporal series of past events. But it doesn't make sense that they have to be completed by successive addition, some sort of dynamical event like that.
Okay, yeah, I see your point. So I mean, even if we consider like one time like trajectory, to say that the events along that trajectory are completed by successive addition will require some overall structure that allows us to define what does it mean for an addition to be successive. Is that the point?
Maybe that, or maybe I say like, no, successive addition requires much more structure than just along one particular world line, but it needs to have some global facts in place about the temporal structure. I mean, I don't know. I just see like, look, I'm none of what I'm saying is in any way questioning what you said. I'm trying to give you even more things to think about that you could actually also challenge other of these premises.
Yeah, I will think about
to
that.
show all of that, really to show that this is a very, very specific way of thinking about temporal structure that seems to be, this argument is soaked with implicit metaphysical assumptions about temporal structure, which really may not be in place. I mean, there's no, I think logically, it doesn't seem to be forced on us. It doesn't seem to be forced on us even physically.
Yeah, I agree with you.
And then the whole argument falls to pieces.
Yeah, I mean, of course, that was my starting point. Now I'm more worried about the parts of non-Penrose cosmology, but yeah, no, but thank you.
Just want to clarify a bit the dialectics of the third part, because CCC is kind of it's tricky to interpret with maximal metaphysical clarity, as we discussed. The status of infinity at the end of one theorem is kind of weird, and I think in a way, right now I think there are two different options on the table. I think we prefer we don't have the same view on that. So one is what I would call the kind of monist view of time. So there is still one time. there will be dual there two types. No, sorry. We need to try again. So since there is a pre-implicated tension between this idea that the trajectories go to infinity with the photons continuing forever, and you also say at some point all the massive matter disappears, so there is a switch and we move on to the next L. So you can almost like you have a kind of first order time that is infinite, but you have a meta time registering when the infinite time stops. So, but that's on purpose, right? Because it's being like this, and it's very difficult to interpret. So one option is to be literalist and accept that it really means it, that it's infinite. But another is to be more relationist and say, well, maybe it's an artifact of the geomachinery, but because it's playing with it and adding those other assumptions, and you no longer have massive particles, it stops to be physical. I think there is another interpretation, which is that it's not really infinite. It's more like it's kind of the apparatus of geologies, but it's not infinite. There is a matter of fact that at some point there is this hypersurface, and there is a finite quantity of spatial temporal distance between us and it. So my question, if you think that's so, to me it's one way to think about that. So maybe it's wrong, and I don't know. I'm just trying to make sense of the situation. So for your dialectic, I think that either you have to show that this is wrong and the right interpretation is the one you presented, or you just show this as a kind of a proof of principle that there is a logical way to make sense of the physics, but you have to show that it's a plausible interpretation, right? I'm just trying to understand whether you are saying that there is room for what you're looking for, or whether you want to have a more a different claim, which is that if CCC is correct, then we do have a demonstration that we have what you are looking for. You see what I mean? So yeah, it's kind of
I think the best I can do is to have something like if CCC is correct and this interpretation of CCC is correct, then we have a traversal of the infinite, right? But for sure, CCC by itself, because it's very speculative and it's very ambiguous in very part, as you said. So, which interpretation is correct? I don't know. I mean, I'm trying to think about it and to.
No, fair enough.
But so to me, there are these two intuitions. One is, well, you make space-time conformal after a certain point, effectively conformal. So basically, what happens is that when massless particles are not around anymore, infinity becomes reachable because it's not at infinity anymore, so to speak. And the other intuition is, well, we can represent that in a physically meaningful way by a conformal diagram that is not just a mathematical way of representing it, but the metric there is really conformal. But actually, there is a way in which the massless particles do an infinity of steps, and we can represent that way if we think about the scale factor. And I'm tending towards this second.
In a way, it feels like a bit like the same issue as the movie Spotlight theory, where you think about time in the four-dimensional term, and then you think that there is also something flowing in it. I think it's a bit some kind of dual structure collapsing in a way.
Yeah, I think there will be more to think about it than to what.
Thank you, Federico.
Thank you for all the feedbacks.